Hey, today we're going to kind of continue our discussion about Riemann sums, but we're going to add another trick to it, another twist. So we have all learned Riemann sum, the three ways for Riemann. And anytime we see Riemann, 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 we think rectangles, right? And we should. Riemann liked rectangles. But we're going to take a look at another method today that is just slightly more accurate tool for us. Not as easy of a formula though. We like Riemann because the area of a rectangle is pretty easy. It's just length times width. So let's say we have this table, and we have this table right here. And we want to estimate the area under the curve. Remember, this integral right here just basically says, hey, find the area. All right? The first question says, use a left Riemann sum. Now, anytime we see Riemann, again, this is a rectangle of 3 intervals, which means this is going to be 3 rectangles for us. So I'm going to split this up into 3 different rectangles. So let's see, the first one from 5 to 8 to 12 and 14. Now the first thing I want you to notice is that the differences aren't all the same. And that is most likely the case that we see most times, that they aren't always going to be evenly spaced. So you got to be really careful when you write out your Riemann sum. So for the first rectangle, we want to use a left Riemann sum. So between 5 and 8, on the left is 5, its height is going to be 6. So I'm going to say between 5 and 8, the height is going to be just 6. Between 8 and 12, 8 is on the left, so that's going to give me a height of 10. Right here. And then between 12 and 14, since 12 is on the left, we're going to use a height of 9. So remember, draw your rectangles. You get a point for that. I give you a point for that. Check. Next, now I'm ready to solve this. So a really cool, fancy way to solve it, since I'm looking for the area, I'm going to write it as an area problem. From 5 to 14, the area from 5 to 14, f of x dx. Now, why do we like f of x dx? Well, remember, there's dx. There's dx, delta x, and there's our f of x. It is a rectangle, length times width. So write this out. It does help, okay? And it's a quick way to write it, because we have to write down that delta x, f of x anyways. This already has it. The only difference is this is not the actual area, because delta x is not really dx. Remember, dx is delta x goes to 0. Since this is obviously not 0 distance between them, this is only an approximation. So I draw my little squigglies right there. So how do I get my values? Well, the width down here, the height is 6. And my width here is 3. Be very careful. They're not all going to be the same. Plus, the next one has a height of 10 and a width of 4. The next one is going to have a height of 9 and a width of 2. Right? Remember, this right here, basically, this is our f of 5 times 3, f of 8, which was on the left, times 4, and this is the f of 12, whoops, we're looking 12, times, f of 12 times 2. Our rectangles. And if we clean all this up, simplify this, we would get 76. Now you don't have to, you can leave your answer like this, or you can leave it like that. Either way is fine. So let's go ahead and do a right Riemann sum. Again, Riemann means rectangles. So when I draw all this out, 5, 8, 12, 14, and this time I'm going to pick the number on the right. So between 5 and 8, 8 is on the right, its height is 10. So now I'm looking at the height of 10. Between 8 and 12, 8 is on the, 12 is on the right. Get lost. Left side, right side. Gotcha. 12 is on the right, so we're at a height of 9. 9, number 9. And then the last one, between 12 and 14, we were looking 14 there. We're going to pick 14, and that's going to have a height of 7. So let's see what we got here. So I'm going to estimate my area between 5 and 14, f of x dx, and it's going to be approximately this time. All right, here we go. The first one has a height of 10, a width of 3. Be careful, the widths are different here. Here my change in x is 3. Here my change in x is 4. Here my change in x is 2. They're not always going to be the same, which is why I'm not a big fan. Like, remember earlier when all these widths were the same? People have a tendency to factor them out. I'm not a big fan of that because then you don't know what to do here. I tutor kids all the time like that, and they're like, oh man, what if they're not the same? What do I do? It's a rectangle. But our teacher taught us to factor it out. It's a rectangle. My head, it's going to explode. So I don't like to do it that way. So I always like to write it. 6 times 3, 10 times 4, 9 times 2. Write it out. It's a rectangle. Length is 10. The width is 3. It's an area of a rectangle. Plus, the next one is going to be 9 by 4 plus 7 by 2. You can leave your answer like this. Or if you simplify that, that's going to equal 78. All right, now, the next one we're going to talk about is way more accurate. So let's think about this. Ready? If I have a function, let's say something like this. And let's say I want to find the area. And I choose, you, Pikachu, the right-hand rule. If I draw my rectangle, man, you can see that there is this huge overestimate right there. So we're not going to be very accurate. So Riemann is nice, provided that delta x, this change in x, is small. But what if delta x can't be small? Well, what else can we do? Well, along comes another method that we like to call the trapezoid method. And trapezoids are very nice because what they do is they look at both sides right here. And if I connect them, if you notice, it's still not very accurate, but look at that error. It is so much smaller. So trapezoids, even though my base may be more spread out, tend to follow the curve more. Like what if I did right here? If I did my right, look at that overestimate. But if I did a trapezoid, I minimize my error. So trapezoids are a very good tool to use for us. And that's what we're going to talk about right now. The trapezoid method. We're still going to use 3 sub-intervals. So we got the 5, the 8, the 12, and the 14 here. But this time we're going to use all the sides. For example, at 5 we have a height of 6. 8 has a height of 10. 12 has a height of 9. And of course 14 has a height of 7. Not on the scale. But this time, instead of using like a left-hand sum or a right-hand sum and get those big errors, what we're going to do is we're just going to connect them and make trapezoids out of them. Like so. And now we can find their areas. So let's see here. The area formula for a trapezoid, 1/2 the sum of the bases times the height. Now remember, the bases are parallel to each other. Okay? All the bases are always parallel to each other. Funny joke, by the way, about parallel lines. Let's imagine you find yourself at a math conference. They're pretty boring. All you have to do is stand up and say, the funniest joke in mathematics. Here it is. 2 parallel lines meet on a plane. Get it? Parallel lines don't meet on a plane. Funniest joke you'll ever hear in math. Alright, so these are my parallels. They're all parallel to each other, so there's my bases. So my first one, this one is now my height. The height here is 3, the height here is 4, and the height here is 2. So to get my area from 5 to 14, f of x dx, it's going to be approximately, it's still not accurate, but it's going to be way more accurate than the other ones. Oops, I lied to you. That should have been 80. My bad. Sorry about that. I added wrong. That should be 80. Alright, so, sorry. Some of you had already caught that. Thank you guys so much. Which is why I never, ever simplify. Now, I'm glad I made that mistake there, because on the AP, they will accept either answer. But if you add wrong, there's a chance you might lose a point. So don't simplify if you're not sure of it. All right, so we get 1/2. The first one has a base of 6, a height of a base 2 is 10, and a height of, what did we say that was? 3. Plus, now my second trapezoid, 1/2, 10 plus 9 times 4. And my last one, 1/2, 9 plus 7, and its height is 2. And you can leave it like this, but if you simplify that, that becomes 78 right there. Now, it's not that trapezoid is the midpoint of them. It's not always the case. That's just the way it worked out. All right, so I hope you guys enjoyed this video here. Oh, wow, we got one more. Let's take a look at this one. All right, a lake has the following shape. Frodo has been tasked to stock the lake with fish. Frodo knows that one fish requires 10 cubic feet of water in order to thrive. Estimate the number of fish that Frodo can stock if the average depth of the lake is 15 feet. So he needs the number of fish. But before he can do that, well, a fish requires 10 cubic feet of water in this problem. So the first thing we need to find is the volume of the lake. Now, it's kind of hard to see here, but these are each 20 apart. There we go. We got to find the volume of the lake. So how do you find volume? Well, that's simple. That's just from geometry. The area of the base times the height. But we're told it had an average depth of 15 feet, so that's our height right there. So this becomes B times 15. So we have to get B, which is the surface area of our lake. So what we can do here is we can do trapezoids. And this is how surveyors determine the area of a lake. There's no equation to find it, but you notice they'll say this lake has a surface area of 20 acres or something like that. 20. So, but they do it the same way we do here. They will go out certain distances apart and they will measure distances across the lake. And then they can use trapezoids to estimate that area. So there's trapezoid 1. Well, the first trapezoid, it's an approximation, 1/2, the first base is 30, the second base is 80, and its height between them is 20. Plus, the second trapezoid, zoids, 1/2, 80 plus 90, times 20. And then the last trapezoid, right here, 90 plus 40, times 20. And if you simplify that, you're going to get 61,500 square feet, because it's the base, right? It's an area, square feet, feet squared. So therefore, to get the volume, we're going to take that 61,500, I can't do 500 yet, and multiply that by, messed that up. Yeah, this is why I hate, there we go. You get 4,100 feet squared, and then when you multiply that 4,100 by 15, you get 61,500 cubic feet. So that's how many cubic feet of water is in the lake. So to get the number of fish, ran out of room here, I'll do it up here. The number of fish, well, each fish requires 10 cubic feet. So you just take that 61,500 divided by 10, and you get about 6,150 fish. Okay, I made up that number. A fish really requires about 1,000 cubic feet of water to thrive. So I made up that number. These fish would probably all be dead because of the nasty stuff that fish do in the water. All right, anyways, messed that up again. That's 2 mess ups there. Hope you guys are welcome. Hope you guys enjoyed the video. Go to part 2. We'll take a look at some more examples. Bye-bye.